Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. Today's talk is by Professor Shivaram Kalyanakrishnan, and he will be speaking on PAC mode estimation using PPR Martingale confidence sequences. Professor Kalyanakrishnan is an associate professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Bombay. His research interests include artificial intelligence and machine learning, spanning topics such as sequential decision-making, multi-agent learning, multi-arm bandits, and humanoid robots. Professor Kalyanakrishnan received a PhD in computer science from the University of Texas at Austin. Subsequently, he was a research scientist at Yahoo Labs, Bangalore, and an Inspire faculty fellow at the Indian Institute of Science, Bangalore. His contribution to a robot shocker have received 2 Best Student Paper Awards at the annual RoboCup competitions. He was also a member of the first study panel of the 100-year study on artificial intelligence, which in 2016 released its report titled Artificial Intelligence and Life in 2030. Before I move on to the talk, I would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links on the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand, unmute yourself, and ask directly, or type them in the chat box, and we'll relay your questions. Over to you, Professor Kalyanakrishnan.
Thanks. So, just turned on my video.
Your screen is not showing the presentation. Okay, I'll stop my video. Now it's okay.
But is my video showing up? No?
Not yet.
Not
we
yet.
Don't see it.
Yeah.
Can you manage without? I don't know. It might be this particular Zoom call. I don't know. For whatever reason, it's not.
It's okay. Continue with the presentation.
Okay. Yeah, I'm sorry about this. I don't know why. Anyway,
there might be some internet
problems are here, so I think that should be sufficient. Yeah. So I'm just recovering from viral fever, so don't be too surprised if I go into a couple of bouts of coughing. I hope it doesn't happen, but it might. Okay, so this is work that was published in AI Stats last year. It's the coming together of many different efforts that I was doing with my students. So Shubham, Rohan, Sanit, Daniel, Inderjeet, Jian, Sushil were all like UG students here. They've all graduated now. Vinay Ribeiro is my colleague. He works in systems, blockchains, and things like that. And Saurav was his student from earlier. So many different things came together, right? And I'm going to give it to you in some, I hope, coherent form. This is an efficient algorithm for PAC mode estimation. So what is mode estimation? So let's consider a categorical distribution. Let's call it P. Categorical distribution means it takes like a handful of values. So this particular distribution, let's say it takes values 1, 2, 3, and 4. Right? It takes 4 values. Now, if you ask what is the mode of this distribution, then by definition, right? So mode is that class which has the highest associated probability, right? So the small panel here shows that you get a 1 maybe 20% of the time, 2 maybe 10% of the time, 3 maybe 40% of the time, right? I've not really drawn the corresponding labels here, but 3, right, clearly is the mode of this distribution because it is the tallest of these bars. The catch that we have is that we are not really given the distribution to look at like this. But the way we have to answer the same question, right, what is the mode of P, is by looking at samples drawn from P in sequence. So really the way that our experiment will proceed is we begin, right, and we say, okay, give me a sample, right, and then you see a 3, and then you say, okay, give me a sample, 1 more, right, and i.i.d, another sample is drawn, maybe this time it's a 1, then again you see a 3, and then you see a 4, and so on, right? You keep going on like this. And so the real heart of what we are asking is, at what point can we confidently stop sampling and declare what we think is to be the mode, okay? Now, this is at a high level the problem we are going to solve. Now, why would we want to solve this problem? It's because it finds place in many applications. Okay, and the reason Vinay is a collaborator on this is because I first started thinking about this when I heard this in a talk from Vinay, who works on blockchains. So what's going on over here? So there is something called a permissionless blockchain. Okay, it's a collection of nodes which you could think of as computing devices. And as a client, right, I can go and ask, let's say, one of these nodes to perform a hard computation for me. For example, I could give it a data set and say, please train a neural network on this. And then using that, you make predictions on this held out data set because I want to use it for something. Right? Or it could be some other computation on database, right? Whatever it is. Now, imagine I did that, right? I went and asked a node, give me the answer to this question. And just for simplicity, suppose the answer that I got back was green. Okay, this node came back and said the answer is green. Now, should I trust this answer, right, and go ahead and do the rest of my life taking green as the answer? In certain situations, maybe yes, right? If this blockchain was one in which the nodes were actually like under some kind of contract to be reliable. But in a permission-less blockchain, it is really like free for all. Anybody who wants can come in. So it could very well be that a node comes in and it takes your money and then it just gives you a quick answer without doing any compute or anything like that, right? So one way you can maybe amplify your confidence in the answer is to go and ask another node, right, to perform the same computation. This time you see a red, right? So now you have your suspicion up, right? Because clearly both of them can't be the right answer. So you go around asking a few more, right? And then at some point, maybe you've seen a few greens, a couple of blues and a red, and you're beginning to feel a little bit more confident that maybe it is green, right? So if it's a reasonable assumption that, I mean, not all of the black blockchain is bad, that a majority of the answer that is the most frequently returned, if we can believe that that's going to be the right answer, then you can, what the problem that you face, right, is that of mode estimation. We have here a distribution over green, red, and blue, right? And we want to find which of these is the most frequently occurring. So this is one application. Another one in the Indian context is with election forecasting. So when we have parliamentary elections, we have 543 seats, right? And what is happening inside each constituency? Each party will have a certain get a certain number of votes, right? There might be a few lakhs of people within each constituency, and we know that the rule by which it operates is within each constituency you just do majority, right? The one that is most gets the most number of votes, right, is going to be the winner of that seat. And you take aggregate overall winners, right? The party that has the most number of seats is the one that's invited to form the government and so on. But then, I mean, this is when the election happens, but very often we want to know the result even before the election is happening, right? So you'll have like surveyors, people going into different constituencies and randomly sampling people within the constituency, right? And based on that, try to project who's going to win in that particular constituency. So again, what they have here is a mode estimation problem. They would like to maybe ask as few people as possible to build a sufficiently confident estimate of who's going to win in that constituency. Okay, so confidently identify winner of each seat by sampling and then aggregate that to get the overall winner. So these are only two motivating applications, but there are a whole number. So I think our paper goes back like 50, 60 years that people have been studying this problem of mode estimation. So here is what I'm going to do to organize the talk. I'll make the problem itself a little bit more formal, and that uses the PAC formulation. And then we will do the simple thing of trying to solve the most simple yet non-trivial version of the problem. That is when the distribution has only two classes. Okay, so it's like the first step in trying to come to grips with solving this problem, understand what works, what does not. But then our main contribution, right, of what we have done is give some understanding of what it means to go from two classes to more than two classes. Right, this is more genuinely going from binary estimation to mode estimation with multiple classes. And somewhat strangely, this was an effort where we did all the practice first, right, and then rationalized that using the theory. It's not like we did the theory and then found the practice for it. It actually went in the other direction. So, in consistent with that, I'm actually just going to discuss the algorithms and their sort of ideas, maybe some empirical results in sections 2 and 3, and leave the theoretical claims for what we have done in section 4 before finishing. Okay, so Ankita mentioned I could take questions in between. So, I mean, I've sort of given you the high-level motivation. Are there any questions? I don't mind taking a couple right now before getting started. Okay, I'll take that as a no, but I'll literally stop like this after each of these sections. Okay, so we can have some questions after each section. Okay, so PAC, as some of you might know, stands for probably, approximately, correct. Okay, it's a very standard thing in machine learning. So how do we formulate this as a PAC problem? So formally, a categorical distribution, to specify that, you give 2 elements. One is the number of classes k, and the other is a probability vector, right, over these k classes. P1, P2, Pk, right? These are numbers that will be between 0 and 1, adding up to 1. So this really for us is the underlying problem, right? The distribution on which we might have to do the mode estimation. An algorithm, right, formally defined, we're going to think of as a mapping from the set of sample sequences, like the sequence you saw, right, 3, 1, 2, 1, 3, right? Every such sequence gets mapped by an algorithm L to one of these k plus 1 things, okay? So the first is saying continue, right? That means the algorithm is saying, I'm not confident enough to stop, right? So please continue, get me one more sample. Or the algorithm can simply stop and say my answer for the mode is 1 or 2 or 3 or k. Okay, so formally this is what an algorithm is. I mean, you could have a randomized algorithm, but for our purposes, it suffices to consider deterministic algorithms like this. What we require in this PAC sense is an algorithm L that for every categorical distribution P that has a unique mode. Okay, distributions need not have unique modes. You could have 2 classes that occur equally, probably, right? But just to simplify life, let's assume that there is a unique mode. So L must be such that whatever P you give it, so long as it has a unique mode, for every mistake probability delta greater than 0, which is also given as an input to the algorithm, L must stop and declare the mode of P correctly with probability at least 1 minus delta. Okay, so you give it any problem and this mistake probability, if it stops and gives you an answer, the probability that the answer is wrong must be at most delta. Otherwise, it should be correctly giving you the mode. Now, you might be wondering where the epsilon parameter is. For those of you who are familiar with PAC, sometimes, right, you will also have like a tolerance. For example, the way to do it here would be to say instead of unique mode, right? You could say, for example, that it suffices to find a class whose probability is within epsilon of the highest probability, something like that. It's very simple to sort of generalize. We just kept the clutter less and made this assumption of having a unique mode. Okay. So it's not strictly PAC. It's probably correct. It's not probably approximately correct the way we've done it. But I think that's not such a big matter. All right. So what we would like is an algorithm that meets this PAC criterion. So this is called the PAC or correctness criterion, the delta correctness criterion. That is non-negotiable. We require only algorithms that are PAC. Of such algorithms, naturally, what we would prefer is algorithms that have low sample complexity. Sample complexity means the number of times they query right before stopping, also called the stopping time. We want that to be as small as possible. Okay, so this is our formal problem statement. We would like to design an algorithm like this and evaluate it empirically, theoretically, and so on. Okay, yeah. So questions about the problem formulation? Okay, all right. So I'm just going to go on then. Okay, now let's wear our sort of hat for coming up with solutions. We know what the problem is. We have to come up with some way of solving this problem, right? Devising an algorithm L for doing it. We'll start in a very natural way. So first, let's focus a little bit more on the special case where you have only two classes. So if you have only two classes in your categorical distribution P, right? Let those classes be 1 and 2. The hidden parameter is only like a single parameter. Okay, if class 1 occurs with probability P1, then class 2 must occur with probability 1 minus P1, right? So the probability of determining whether 1 or 2 is the mode is the same as asking whether P1, this unknown parameter, is greater than half or it is less than half. Right? Accordingly, one of these two things will be the mode. And this we have to answer based on observing this sequence of samples, right? 2, 1, 2, 1, something you see like this. And at some point you have to stop and say 1 is the mode or 2 is the mode. So how might we do this? For anyone who's familiar with this kind of estimation, I mean, it's very, very sort of textbook, straightforward. So what we could do is there is this one Bernoulli parameter, really, right? That we're saying like ones and twos, which are literally like the outcomes of a Bernoulli with probability P1, right? So you could use your knowledge of confidence concentration inequalities like Heffding's inequality and maintain lower and upper confidence bounds on this unknown parameter P1. Shortly, I'll tell you concretely how to do it, but imagine that we have some black box for drawing lower confidence bounds and upper confidence bounds. So it might proceed something like this. After P samples, let P hat T1 be the empirical fraction of class 1. Okay, that's like the number of times you've seen class 1 divided by T. Okay, that number is P1 hat T. Now we can, using some confidence bound, right, say that this is what P1 hat T is. And here is what I think I'm sort of confidently be able to say as an upper confidence bound for P1 and a lower confidence bound for P1. Okay. This UCB and LCB will also depend on delta, right? The mistake probability that we are using. So maybe after 7 samples, your picture, right, with the empirical mean and the lower and upper confidence bounds looks like this. Typically, what will happen is as you get more data, right, after 20 samples, maybe the mean went up by a little bit, the empirical mean, and these bounds came a little bit together. They shrank, right, because we became a little bit more confident. And then after 100 samples, it has shrunk down even more. But you see that it's not like either of the upper bounds are separated from half, right? The UCB is above half, the LCB is below half. We're still not good to stop. But at some point, right, it will happen with sufficiently high probability that the UCB will fall below half, right? Or the LCB will fall above half. Imagine that this happened for us after 348 steps, okay? If this happens, so long as we have drawn these confidence bounds using a rigorous formula that can be reasoned with, we can stop, right? And say that in this case, we will say that P1 we think is less than half, right? So 2 is the mode, not 1. Okay, now this is just an illustration. This is very typical of how you might set this up and solve the problem. One thing to note over here is that the stopping time is random. Okay, even if this is the rule that we're going to apply, we have a fixed formula for applying this lower and upper confidence bounds. Ultimately, the stopping time gets decided by the random zeros and ones outcomes that we get, right, from these draws. So it could stop at different points of times on different runs. Now, this becomes a little bit problematic when we apply directly things like Heffding's inequality, because a prerequisite for applying those is that the number of samples is fixed. It's a constant before you can apply it. So to deal with that, we very often apportion this mistake probability over time steps. Okay, and this is sometimes what is called a union bound, just to make sure that mathematically what we're doing is correct. So you could run exactly what I showed on the previous slide by using this formula for LCB and UCB. It's the empirical mean plus or minus this beta quantity here. And beta depends on the number of samples, right, as well as delta. K and alpha here, don't worry about it, they're just constants. You could use something a little bit more sophisticated. You could use empirical variances in the returns. This is using something called an empirical Bernstein bound. One particular reason I'm showing it here is that this particular algorithm, right, that does mode estimation using this empirical Bernstein bound, that really was the baseline that we were comparing against. This is work that was also done at i.i.d. Bombay in the lab of my colleague Nikhil Karamchandani. We're going to call this algorithm A1. Okay. These are both doing what is called like a naive union bound. There are slightly more sophisticated approaches to deal with the fact that this stopping time is random. Again, quite standard in the literature now. There's something called a self-normalized inequality and so on. Okay, so what I have told you now is a very natural approach to try and decide, right, whether this unknown parameter P1 is less than half or greater than half in a PAC sense. So that when we do it, right, the mistake probability we have is at most delta. An alternative to doing it like that is to do it using PPR Martingale confidence sequences. Okay, so this is one of the, I don't know, secret sauces in what we do. It's not really secret. I mean, it's it's there, it's published and so on. But this is not our work. We were sort of just piggybacking off some fresh work that was available at that time. It came out of Carnegie Mellon. This is due to Waudby-Smith and Ramdas. So this next 5 to 10 minutes, I think is of independent interest. It is not really only for mode estimation, but it is something that is more generally useful if you're trying to estimate parameters by from data and so on. So let me explain how this whole approach to confidence sequences to.
I have a question.
Yeah,
So in
yeah.
the previous slide, the number of samples, how we are fixing it, is it predefined or?
No, so at time t, you draw lower and upper confidence bounds based on this formula. Okay. If you have separated from half, then you stop. If you have not separated, then you just continue. So t will become t plus 1.
Okay.
And then you just keep going like this till you separate. And therefore, that's the reason you don't know how long it will take to separate, right?
Yeah, so we cannot guarantee this low sample complexity.
You cannot guarantee any fixed constant sample complexity. It will have like a random stopping time. Yes.
Yeah. Okay.
Okay. So how do these PPR Martingale confidence sequences work? So here is what we do. Okay, we have this unknown parameter P1. We are going to adopt what looks like a Bayesian approach, saying we don't know what this parameter is. So we're going to assume that we'll start with some prior for this parameter, and then as we get data, we will, consistent with Bayes' theorem, we will update our prior. So we know that P1 is a parameter that's going to be between 0 and 1, right? So we can actually start with any prior subject to some constraints, but for simplicity, right, let's just assume we start with the uniform prior. So uniform prior means we are maintaining at any point of time a probability density function. Okay, that's what we're calling pi. At the very first time step before anything has happened, that is pi 0. And for any parameter q between 0 and 1, right? This q variable is just to talk about the PDF. Pi 0 of q is 1. But now when we start getting samples, right, from the Bernoulli, right, this 1-2 distribution, we do an update, right? We refine our current belief based on the data that got generated, right? And this is standard, right? Posterior is proportional to prior times likelihood, right? So the posterior pi t of q is going to be pi t minus 1 of q times what is the likelihood that xt, right, the actual data got generated. So suppose xt was 1, right? The probability that that would have been generated had the actual prior been, had the actual mean been q, would be q itself. And if a 2 got generated, the probability that q would have generated a 2 as an outcome would be 1 minus q, right? So this is the exact sort of update formula to go from pi t minus 1 to pi t. The denominator here is just to make sure that pi t remains a probability density. This is just the standard Bayesian update. We start with uniform prior on P1. As we start getting data, right, which we know is coming because of P1, we refine our belief distribution accordingly, consistent with Bayes' rule. So pictorially, here's how it might look. What I'm drawing here is this pi. Okay, so at p equal to 0, right, before anything, pi t of q is just going to be this uniform prior at 1, right? It's like uniform distribution with support between 0 and 1. So after 10 trials, suppose we saw 8 ones and 2 twos, then the prior distribution is going to go a little bit like this. Okay, it's going to peak closer to 0.85 or 0.9 or something like that. It's going to have very little mass close to the left-hand side. Suppose you see 100 trials, out of which 80 are ones and 20 are twos. It starts peaking a lot more, right, around 0.8. Okay, so I'm not really given you the entire story yet. What we have done so far is we have maintained a belief distribution on P1. Okay, now for a bunch of definitions, define the prior-posterior-ratio, okay, at time t as RP of Q. Okay, so this is for all Q between 0 and 1. To simply be the ratio of the prior, right, which was phi 0 of Q, divided by the current belief distribution, the posterior, which is phi t of Q. I mean, in fact, for us, this was just 1. In general, it need not be, but it could be. So RP of Q is called the prior-posterior-ratio, or PPR. Now, define this set CT. Okay, it's called the confidence set. CT is the set of all those Q for which RP of Q, this prior-posterior-ratio, is less than 1 over delta. Okay, it's just defined to be that. Now, it turns out that if you've defined prior-posterior-ratio like this and your confidence CT, then we have the following guarantee, which is a very useful anytime guarantee. Okay, the guarantee is that the probability that there exists any point of time where P1 did not fall into CT, right? That P1 actually fell outside of the confidence set at that point. That probability over all time, okay, that there exists here is inside of this probability. That entire thing, right, is upper bounded by delta. Okay, so typically with Heffding's inequality, you'll get a similar guarantee, but you get it for each point of time. Right here, we're simultaneously getting it for all points of time, which is why this is called an anytime guarantee. And this is very useful. Okay, this allows us not to be worrying about the union bound and things like that. So pictorially, okay, let me show you that maybe on the next slide. The way we get this guarantee is, again, this is not our work, but the way it works is you can sort of show, right, without too much fuss, that if you evaluate this prior-posterior-ratio at the true parameter, which is P1, then RP of P1 will be a martingale. Okay, and because it's a martingale, you can apply known results on martingales, including something called Bell's inequality, and from there, right, it will follow that this anytime guarantee holds. Okay, and as I said again, there is nothing very specific to mode estimation. You can use this much more widely. Okay, but anyway, let's see how this works in our case. I already showed you the top 3 graphs where we were looking at the posterior distribution after t equal to 0, 10, and 100 samples. So what is the PPR, this RP? It is essentially 1 over pi t, right? Because our prior distribution was just like the uniform distribution. So RP is what I'm drawing here in blue, right? So with 0 samples, it's again just this line. But then as you start getting more and more samples, you can see that the blue is changing quite substantively. Suppose we're going to run this with delta equal to 0.1. Then 1 over delta is 10. So what we are drawing as our confidence bounds as we go along is, at this point of time, after we've seen 10 samples, what we're going to say is we are sufficiently confident that the mean lies between, I don't know, 0.42 or something like that here, right? And something close to 1. Okay, we are quite confident that the mean does not lie this side of 0.4. It's become much more concentrated. Our confidence bound is going to be somewhere between 0.7 and 0.9 or something like that, right? After we've seen 100 samples. So the particular formula, right, for drawing the confidence bounds comes from RT of Q and it being compared with 1 over delta. Okay, I just have one more slide on this before I stop for questions. So it turns out that the way to do the belief update, if the data was actually coming from a Bernoulli, which it is for us, it turns out that the belief distribution is properly represented as a beta distribution. Okay, beta is a standard family of distributions. So if we apply the PPR stopping rule, right? So if we derive our stopping rule based on this PPR idea, then here is how it works out. Okay, so at time t, let first of t denote the class that is most frequent. I mean, we have only two classes now, so let it be the more frequent class, and let second of t be the less frequent class. Let STI be the number of occurrences of class I. So ST1 is the number of times class 1 occurred, ST2 is the number of times class 2 occurred so far in the data. So then our stopping rule, it turns out, is very sort of simple and elegant to state. So what we need to do is consider a beta distribution whose parameters are the number of successes of the first class plus 1 and the number of successes of the second class plus 1. Okay, so beta has two parameters, alpha and beta. Just like a Gaussian has mean and variance, right? Beta distribution has these two parameters. These are both, I mean, very easy for us to, we're just counting the number of occurrences, right? If we measure the PDF of this beta distribution at half, if that turns out to be smaller or equal to delta, we can stop and return first as our answer, as the mode. If, on the other hand, this quantity is greater than delta, then we should continue. Okay, we can't stop. So this literally is the mode estimation rule that we have. We're going to call this PPR Bernoulli. Okay. PPR Bernoulli. Okay, should I stop for questions? Yeah, maybe I'll stop for questions if there are some. Because I've said a little bit about the methodology here. Okay, anyway, I think next stop is only like 2 to 3 minutes away, so I'll just go on then. So the first thing we naturally did is empirically evaluate how good this stopping rule is. Right? We know that it is correct, right? Because simply by piggybacking on the existing correctness of the PPR approach. But then when we went and empirically measured, I think it was very clear that it is significantly superior empirically. So what's being plotted here in this graph is the sample complexity of stopping time on different problem instances. You can see what's varied on the x-axis is P1. Okay, it's this unknown parameter. And this is an experiment with delta fixed at 0.01. So we know that there's a lower bound on this. Okay, from information theory, there is a lower bound saying you need at least so many samples. So that lower bound is the sort of small lowest of these graphs. But the one that's closest to it is green. Okay, and that is PPR Bernoulli. And it does much better than the hefting-based rule, the self-normalized rule. It also does much better than this A1, right, which is using the empirical variance and so on. So there's a very clear sort of trend here of PPR Bernoulli doing quite well in practice. And this is also validated when we keep P1 fixed and vary delta, right? So delta is varied here on logarithmic scale. Again, this y-axis is sample complexity. You can see that right next to the lower bound is PPR Bernoulli, right? Then you have this KL and hefting and all of these different rules. So I think there's a very clear message from the data that PPR Bernoulli, which is correct, also works extremely efficiently. Okay, yeah. Now I will stop for questions and also for drink of water. Okay, if there aren't any, I will go forward. Actually, I just need to make sure we are there. Ankita, is the call still on?
Yes, yes. I think there are no questions, so please go ahead.
Okay. All right. Okay. Okay. So now we consider the more general problem of mode estimation when you have more than two classes. Okay. So what is the generalization we're looking at? We're not looking at only ones and twos anymore, but we're going to look at a stream like 3, 1, 3, 4, 2, 1, right? Which has got multiple classes. So what we did was consider two very natural ways of using our two-class solution as a black box for multiple classes. Okay, and these are also very standard in machine learning, even otherwise when you have multiple classes. So the first is called a one versus rest approach. Okay, so here is what we will do here for each class I. Okay, remember that we have k classes. We will try and estimate the underlying probability pi. Okay, and as soon as the lower confidence bound on some pi, right, exceeds the upper confidence bounds on all the other classes, pj, j not equal to I, then we stop, right, and say that class I is our mode. Okay, and the particular formula to draw these confidence bounds for each is exactly what we've done earlier, right? For each class, right, when you get this stream of samples, you're either getting a one here or you're getting a not one, right? A not one means that is data to say that this P1, right? I mean, it is in fact a Bernoulli. You can think of deriving like k Bernoullis out of this one for each of the classes, right? That's precisely what you would do, and see this one versus the rest approach, and stop at a point where confidently one of the means has exceeded all the other means. The contrasting approach is we compare these classes pairwise. Okay, so between every pair of classes, we try and ask, is one class occurring more frequently than the other? So this is called like one versus one. So between pair of classes I and j, consider this parameter qij being pi divided by pi plus pj. Now we can act, suppose when we're comparing, let's say 3 and 2, we can simply ignore all the 4s, all the 1s, everything that's not a 3 and 2, right? Just focus on the subsequence of 3s and 2s, right? And ask, is 3 occurring more frequently than 2? Is the frequency of occurrence of 3 inside of that, right, greater than half? So it is that parameter that is this q. And we stop and declare I, class I, as the mode if for all j not equal to I, qij confidently exceeds half. Okay. Now, these are, of course, two different approaches. Now, one thing to note, right, qualitatively is in the one versus rest approach, every time we get a class, right, the next sample that we get, all of these p estimates are going to change, right? Because for one of the classes, it will be a positive example. For all the other classes, it will be a negative example. They will all change. Here, on the other hand, right, in one versus one, suppose we get next, let's say a one next, right? It is only the Qs corresponding to one, like 1, 4, 1, 3, and 1, 2 that will get updated. Q3, 4, Q3, 2, and so on, right, are not going to get updated. So it does feel that one versus one, right, is not really updating all the time, all the samples, all the estimators that we have. So is it wasting data? Well, it might be, but the proof of the pudding is in the eating, right? So again, the thing that we did is we took these two approaches and implemented them and saw what happened. And we got, again, very, very definitive results. So each row here is like a probability distribution. So P3, for example, is a probability distribution where one of the mode has a probability of 0.2, and there are 8 classes with probability 0.1. Okay, and similarly, you have like various other classes with different values of k. And here is what we saw. It doesn't matter which algorithm we apply, right? A1, KLSN, PPR. In each case, the 1 versus 1 does significantly better than the 1 versus rest. Okay. It is also the case that whether you're doing 1 versus rest or 1 versus 1, PPR is doing better than the others. That we've kind of already seen. But even when we go from 2 classes to multiple classes, 1 versus 1, right? For each of these is doing, in terms of its sample complexity, is incurring fewer samples than 1 versus rest. There is really no exception here. It holds for all of these different problem instances. So normally you don't get such conclusive results, right? But we got it, right? So then we had the job of rationalizing it, explaining it, and so on. So
are these number of samples?
yeah, this is the sample
Okay.
complexity.
Okay. And that QIJ confidently exceeds 0.5 means both LCB UCB exceeds 0.5, right? For QIJ?
No, either the LCB exceeds 0.5 or the UCB falls below 0.5.
Okay.
Yeah, it must be on one side of 0.5.
Yeah, okay. Either of them. Okay.
Right. Okay, now before sort of moving on to analysis and so on, let me just assimilate this into like a very concrete rule that we can apply when we have like multiple classes. So the idea is that we stop in this 1 versus 1, right? We're going to start calling this PPR 1v1. We stop when some class I beats all classes j not equal to I, right? This is what we had decided to do. But I mean, we can observe that if at all we're going to stop, right? Clearly, the I that is going to win and so on is going to be the most frequently occurring class, right? It's going to be first of T. Now, moreover, if first of T beats all other classes, then first of T must beat second of T, right? That's just like a logical statement because second of T is also another class. It is also not very hard to show by just writing down our formula that if first of P beats second of P, then it must be beating everybody else because the other classes will have fewer occurrences. So it actually turns out that even if we must be monitoring all pairs, right, which are like K choose 2, it suffices for us to implement this rule to just see whether first of P is beating second of P or not. Okay, so again, this distills down into a very simple rule. So we can stop and declare first of T as the mode if and only if the beta distribution with parameters first of T plus 1 and second of T plus 1, their number of successes evaluated at half is less than or equal to delta divided by K minus 1. Okay, when K was 2, right, we just call this delta, but in general, it turns out the generalization is simply using delta over K minus 1. Okay, this is our rule which we call PPR 1v1. This is very quick, easy to compute. The fact that this beta distribution is at half, right, actually means we can compute this exactly with a few sort of multiplications. And especially compared with many other rules which involve solving numerical problems and so on, right? Even practically, this is much preferable. Okay. So this is our rule, and I've just sort of shown you already that it works very well. So what's coming up is some understanding of why it works well, some justification for the fact that 1 versus 1 is doing better than 1 versus rest, and so on. Okay. So yeah, before I go into this, are there questions? All right, so I'm then just going forward. Theoretically, what are we able to say about PPR 1 versus 1? So like any problem in computer science and algorithms, whatever, right? We want to compare ourselves with the lower bound. So the existing lower bound for mode estimation came from this 2020 paper that introduced also that K1 algorithm. So this is sort of result coming from information theory that any delta correct algorithm for this PAC mode estimation, right? It requires at least lower bound of P delta samples. So suppose it is run on distribution P, right, with mistake probability delta, it needs at least this quantity in expectation. Okay, and what is this quantity? This quantity is something log 1 over delta. But what is that something? Now let's consider every distribution P prime that is different in its mode from P. So P has a certain mode, right? Let's consider, so suppose we're talking about 5 classes. Consider every other 5 class distribution for which the mode is different from the one of P's, okay? And out of all those distributions, you pick the one that has the smallest KL divergence with P. So the quantity here is 1 over KL divergence between P and P prime being a distribution from that same sort of family, right, but which has a different mode. Now, this is known to be a lower bound on the number of samples that we need in order to be like a PAC algorithm for mode estimation. Okay. Now, the result that we are able to show for PPR 1v1 is that PPR 1v1, suppose on given distribution P and mistake probability delta, the expected stopping time, right? The average time it takes to stop is tau of P delta. Okay. Then we are able to show that if you take the ratio of tau of P delta to this lower bound, then as delta goes to 0, right? This is like an asymptotic result. Delta goes to 0 is the same thing as 1 over delta goes to infinity, right? As the delta becomes smaller and smaller and smaller, the upper bound essentially converges to the lower bound. The ratio goes to 1. I mean, this is really like you can't. This limit cannot be less than 1, right? Because then that would mean that we are violating the lower bound. The least it can be is 1, right? And it does become 1. It doesn't become 1 for all finite time, right? But it does become 1 as delta goes to 0. So this is a fairly useful, convincing result. And again, our way of proving this is not very original. This similar type of analysis has been done with bandits, right? So we piggybacked on some existing analysis from Garibier Kaufman, who have like a similar asymptotic result with bandits. But this asymptotic optimality also shows up actually practically. Okay, so what we're plotting in this graph is actually the ratio. Okay, it is the empirical sample complexity to the lower bound. Okay, and we see what this ratio becomes as delta is taken from 10 power minus 11, right, all the way down to 10 power minus 200. Okay, so delta is decreasing as we go from right to left. And the theory tells us that the ratio, right, actually should go to 1. And you can see that for PPR 1v1, right, in orange, the ratio almost sort of it is at 1. I mean, you have to zoom in over here. That's what we've done in the inset. KLSN is another algorithm that seems to be close to 1. But many of these 1VR algorithms, right, A1, 1VR, even PPR 1VR, right, the asymptotic thing does not go to 1. It goes to some other constant. Okay. So this is yet another sort of validation that PPR 1v1 actually is extremely efficient in practice. There's yet another theoretical characterization of 1v1 being a better choice than 1 versus rest. So we decided to call this uniform domination. Okay, I'll explain what this is before telling you what the result is. So let x equal to x1, x2, x3, etc. be an infinite sequence of samples coming from P. Okay, it can be any, it can be 3, 1, 2, 4, 3, whatever it is, right? So for any algorithm L, let TLX denote the stopping time of L on X. If X was actually the sequence, at what point would L stop on it, right? How long would that sequence be? That is called T of LX, okay? And let us define algorithm L1 to uniformly dominate algorithm L2 if for every sequence as well as every mistake probability delta, if L2 terminates, right, if T of L2x is less than infinity, that means it stops somewhere on X, then L1 will stop no later, okay, it will stop before, right, or it will stop latest at T of L2x, right? So T of L1x will be less than or equal to T of L2x always. assuming both of those things are not infinity, because there could be sequences where neither of the algorithms stops. Okay, so pictorially, here's how it might look, right? You have the same problem, but because of randomness, the first time you run an algorithm on it, right, you might see 2, 1, 3, 1, 2. Another time you might see 1, 3, 1, 3, 3, right? These are all the possible X's that can come when you run your algorithm. So suppose L2, right, stops at this point on this sequence, this sequence, and so on. L1 uniformly dominates L2 if the picture looks like this. That L1 is always occurring before L2. Worst case, it can occur on L2, but yeah. Okay. Now, we have been able to prove the following results. Again, reinforcing that 1v1 is a better choice for mode estimation compared to 1.
Is it true for every sample path?
See, there could be sample paths where neither algorithm terminates. So suppose we're doing mode estimation with just 2 classes, and you just keep getting 1, 2, 1, 2, 1, 2, 1, 2, right?
Yeah.
You will never be confident enough to terminate. So that could happen, but if you have like a fixed problem instance, the probability of you getting such paths, the probability on such paths will become 0.
Okay.
Yeah. Right. So we are able to show that hefting, right, 1v1 uniformly dominates hefting 1vr. Okay. So provably, right, we can theoretically show that if on a particular sample path 1vr has terminated, 1v1 ought to have terminated before. Similarly, we have shown that A1 1v1 uniformly dominates A1 1vr. PPR 1v1 uniformly dominates A1 1v1. The natural question to ask is, does PPR 1v1 uniformly dominate PPR 1vr? Right. So we think the answer is yes. We've done like numerical tests to know that this is actually true up to I don't know 1,000 samples or something like that, but we don't have a proof. Okay. One reason we get stuck with this proof is it has to do with this beta PDF that is full of integrals and factorials and all of that, right? So we've not really been able to penetrate and formally show it, but we are actually, I'm certainly convinced that this is true, but it doesn't have a proof yet. So if someone's interested, feel free to take a look at, it's there in one of the appendices in our paper, right? As a conjecture, you can try and prove it. And these proofs are done very straightforward. It is literally logically just writing down the termination condition and showing that one L2 terminating leads to implies L1 terminating. Okay, so let me finish because I think we are more or less there in terms of time. What we've done is we have looked at the problem of PAC mode estimation and applied this relatively recent idea of PPR Martingale confidence sequences to solve the PAC mode estimation problem. In particular, technically, the main benefit it provides is not having to worry about the random stopping time. The biggest, I think, contribution of ours, right, is to give some guidance on how to go from 2 classes to multiple classes, and we are very sort of convincingly shown that 1 versus 1, right? Just monitoring pairwise is a better idea than doing 1 versus rest, where we're trying to estimate each class's occurrence probability. PPR 1v1, the final rule is simple. It's asymptotically optimal. Practically, it works quite well. Those 2 applications that I started out with as motivation, we've actually done some further experiments. I didn't want to bring it into the talk, but I mean, we have sort of enough to show that practically using this rule, right, makes enough of a difference by a factor of a few things, right? It's not orders of magnitude better, but it's factor of 2, 3 better, and practically that should make a difference. All the code is there. GitHub, the link is there in the paper. There's one unresolved conjecture about 1v1 PPR implying PPR 1v R termination for those who are interested. There are certainly many more applications of this PPR Martingale confidence sequence that I think where it could help. Bandits would be one of them. But yeah, if I don't know if you're anyway sort of working with other applications, including online learning in general, but mode estimation in particular, do consider using PPR Martingale confidence sequences. Good. Okay. So now I think I am done. So any final questions?
one question. Does this work help us to calculate the second mode, or the second most frequent value, or actually the distance between the mode and the second most frequent?
Okay, so I think it will help to see that picture. So you're saying you would like to estimate P3 minus P4?
Correct. So as to have some kind of value or confidence between the predicted mode and the next best.
Yeah, I think it should be possible. I mean, using this apparatus, you would have to maybe just monitor a different quantity. I'm pretty confident the answer is yes, because once you draw lower and upper confidence bounds, right, you can sort of innovatively use them in many different ways. If you're trying to estimate this gap, I think it should be possible. Yeah, and in fact, we don't particularly need PPR using even like Heffing's inequality. I think you should be able to do it. And maybe you'll be able to do it more efficiently if you use PPR.
The reason like why I'm asking this is, suppose you are given like a budget of sampling complexity, that you have a population and you can sample only that maximum this much number of time. I want to evaluate how far off my mode estimate is from the next.
Could you repeat? You want to estimate how far your mode estimate is from
the next most likely, like the second mode value? How far off can I be from the actual value? Is the something that is predicted? The delta that you may actually get from a fixed sample complexity.
Right. Yeah. So you instead of giving delta as an input, right, what you're saying is you'll fix the number of samples, and what you would like is some kind of I don't know, confidence at the end of it, saying how on the gap between the highest and the second highest.
Correct. Yeah.
Yeah. So see, this kind of thing has been done a fair amount in the bandits literature. So even in bandits, there is this PAC formulation similar to what I have shown, and there's also something called simple regret, right? Which is a problem where the budget is specified and you're trying to minimize in that case, it's with bandit arms, right? So you want to give an arm with a high expected reward. But yeah, I'm not able to sort of give you the answer exactly as it is, but I mean, I'm reasonably confident that you spend some time staring on it, right? You will be able to come up with some rule to both formulate exactly what you're saying and to make some claim for it.
Thank you.
Okay, if there are no more questions, we can close this session. Thank you, Professor Kalyanakrishnan, for an informative talk. And if you are planning to visit ISC in near future, please let us know. We can have an offline talk.
Sure. Yeah. Thank you.
Thank you so much.